So you probably realized by now that uncertainty, also known as error, um, is important to me. And it's important to me in GIS because there's two main problems that I see that folks get into with GIS data when they start doing analysis. The first one we've talked quite a bit about, which is spatial references, especially having the wrong spatial reference attached to a set of data or a missing spatial reference. And the other one is having data that isn't of the required accuracy that they need for the task they have in front of them. Both of those are big problems. I'm going to start talking about uncertainty by the two major components of uncertainty, which are accuracy and precision. On the left, we have a target with high accuracy but low precision. On the right, we have low accuracy and high precision. And I really like these symbolically because it shows me that high accuracy means we are on target. Okay, it means that we are getting the results we expect. We just don't have really good precision or repeatability. Where with low accuracy, we're off target. We're having some bias where our data is shifted, but we have high precision or high repeatability. Both of these are important. If you do any target shooting, you will probably immediately realize that high precision with low accuracy is easier to correct for. If you know you have low accuracy and you know what's happening with your accuracy, you can literally shift where you're pointing over and up in this case, and then you're have higher accuracy. So it's easier to fix an accuracy problem than it is a precision or repeatability problem. Okay, so formally, accuracy is the distance from truth. And I have seen these terms not being used correctly even in published literature, so feel free, take a look. I'm almost positive this is what they mean. Accuracy is the distance from truth. Now, we never really know what truth is, but we can get reference values or values of much higher accuracy so that we can measure how accurate our data is. And that's what I recommend everybody do. Precision, again, is repeatability. Now, this is represented by this chart showing that if this is our data, our distribution of the data, precision is going to be the width of the distribution. Okay, you might already see where I'm headed with this. Accuracy is going to be how far off truth we are. Estimating precision, most commonly by far, is standard deviation. Standard error can also be used for precision, as well as confidence interval. So all three of those are ways of doing precision. Min-max is another way to do precision. I just don't recommend that one because usually min-max isn't really accurate in that you can have values well outside the min-max. And it doesn't really tell us what's happening statistically with the data. Now, to keep your precision high, a couple things you need to do. One is make sure you use significant digits correctly. I recommend just keeping all the significant digits you have until you actually publish your final reports, and then report the appropriate amount of significant digits. Also, make sure that your data types in your attributes or anywhere else where you're storing data in the computer that you use doubles and long integers. If you use those, the doubles will be 64-bit floating point, and the long integers should be 64-bit or at least 32-bit integers. So in either case, you should have enough bits there to represent significant digits you need. And then when you report it appropriately. Don't report more precision than you actually have. Okay, standard deviation. We use this all the time. It's just this magical thing that happens in the natural world, is that because of the randomness in the natural world, we tend to get standard deviation plots out. That's just what data tends to do. And you will see that with your GPS. If you take enough points, you'll get a nice standard deviation curve. And we'll see these throughout as we work with spatial data. They just happen to appear. Not all the time. There's other distributions, gamma distributions, all kinds of different distributions depending upon the nature of your data and the nature of the uncertainty in it. A couple confusion points about standard deviation. We'll talk about 1 sigma, 1 standard deviation away from the mean. So this is the mean, 1 standard deviation, 2, 3. Often I ask students how much data is within 1 standard deviation, and some students will say 1/3. It's like, well, actually, it's on both sides, right? So it's 2/3 are within 1 standard deviation. Another question I like to ask is how far does it go out on either side? It actually goes out to infinity. This is one of the reasons min-max doesn't really work, is because if you have data that is distributed with standard deviation or most other distributions we use, you could get a point way out here, way off to the side. Okay, it's very unlikely, but it could still happen. And a min-max doesn't represent that well. Okay, onward. So for accuracy, we don't have as many measures being used. The one that I see used the most, especially in the engineering community where I came from, is RMSE, or root mean squared error. I'll mention this in the lab videos and show you the Wikipedia page. There's an excellent Wikipedia page on it, and this is the equation for it. And again, there are other measures, but this is the one I see used the most. Now, I don't see RMSE used heavily in natural resources. I hope to see more of it. It's very similar to standard deviation. It just has this value from a higher source of accuracy. So that's really the problem with computing accuracy, is we have to have that higher source, and we don't always have that. And that's the reason I've structured the labs where you make your own higher source, which you could do with any field equipment. You may have to do it before you go out in the field. There may not be something in the field that you could see from satellite or aerial photography. And then you've got that estimate of what your accuracy is.